Now let's look at another graph algorithm. This one's called Prim's algorithm, and it's used to find minimum spanning trees of a undirected graph. So this time our edges are not going to have directions. They're undirected. That basically means that they go both ways, meaning you could travel along either direction on this edge. But what exactly is a minimum spanning tree? When we learned about the basics of trees, we learned that trees are undirected connected graphs. Undirected means that the edges don't have direction, but usually in trees they do have directions. For example, binary trees usually have pointers that just point to the children. But usually we ignore that fact when we're talking about binary trees and stuff like that. But in this case, it's a bit more strict, meaning the edges really will not have any direction. The other thing is that it's a connected graph. That means that all the nodes should be connected together. There should be a path from one node to another node, and that's true for every pair of nodes in the entire graph. So for example, if we had some nodes like this and then a third node over here that's not connected to the other nodes, this is not a connected graph. They all have to be connected. We'd have to introduce an edge like this, which connects all of them together, or maybe an edge like this. But there's actually one last thing that defines a tree, and that is that the graph has to be acyclical. That means that the graph cannot have any cycles, of course. So based on this criteria, do you think this graph forms a tree? Probably not, because we definitely have some cycles. That's a cycle, that's a cycle, there's a cycle here. There's a bunch of cycles actually. So this is definitely not a tree. Therefore, it's also not a minimum spanning tree. But what exactly is a minimum spanning tree? Well, given a graph like this, we want to take a subset of the edges that form a tree based on this criteria, but we want to do so such that we minimize the total cost. In this case, it doesn't look like the edges have a cost, but if they did, we would want to take a subset of the edges such that the total cost is minimized. First, let's take a look at an even more simple example. So suppose we're given a graph like this one and we want to find the minimum spanning tree. So we want to take a subset of these three edges such that we do connect the entire graph without forming a cycle, but also so that we minimize the total cost of the edges. The reason this might be important, basically an application of this would be maybe we have a bunch of computers, or maybe these are cities or something, and these edges represent the cost of connecting these cities together, or maybe the amount of road that we would have to create to connect these cities together. And we want all the cities to be reachable from one another, but we don't necessarily need, every edge to exist here. That would be one example of an application of the minimum spanning tree algorithm. It's definitely a bit more abstract than the shortest path algorithm. But for this example, what would the minimum spanning tree be in this case? Well, it's pretty straightforward. We would simply not need this edge, meaning if we have this edge, we have connected B and A to each other. If we have this edge, we have connected B and C to each other. But also C and A are reachable from each other. The path, connecting them costs a total of 3. We could have, if we wanted to, included this edge, but we can't include all 3 of these edges because then we have a cycle. So we have to remove at least one of them. We could have removed this one, but then the total cost is 4. We could have removed this one, but then the total cost is 5. So the best way to minimize it is simply like this. Also notice how we have 3 nodes here, and to connect 3 nodes together, it only took 2 edges, and that idea is actually pretty consistent. If we have n nodes and we're trying to connect them all together without forming a cycle, it's always going to take n minus 1 edges. That's just always going to be the case, as long as we don't have a cycle, because the intuition behind it would be like this. When we just have a single node, we have one node and we have 0 edges. When we have 2 nodes, to connect them together, we need at least 1 edge. So we have 2 nodes, but 1 edge, and this is connected. And then if we add a third node, we have 3 nodes, and to connect them, we need 2 edges. So this would be one valid solution. And we could keep going. But of course, if we add an extra edge at this point, there's only one that we could add over here. This would then no longer be a tree. If we have 3 nodes and 3 edges, that's not a tree. And the same thing happens if we have 4 nodes. So at this point, we have 4 nodes, but we have 3 edges. It's connecting them all together. But if we introduce a new edge, whether it's here or here or here, we're going to end up with a cycle. So the idea is that to have a tree of n nodes, we need n minus 1 edges. Also notice how, if I change the weights of these edges to be this, what would the minimum spanning tree be? Well, regardless of which edge we remove, our minimum spanning tree has the same cost, and the graph is still, of course, connected and acyclical. So we could do it 3 different ways. So what does that mean? Well, that means that there are actually multiple valid solutions for a minimum spanning tree. And that's perfectly fine. So if there are multiple solutions, we can return at least one of them. It's not too different from the shortest path algorithm. In a graph, there might be multiple shortest paths connecting, 2 nodes together. It could have been possible that, this path has a cost of 5 and this path has a cost of 5 as well. So in that case, there would be multiple shortest paths from C to D. That's perfectly fine. We just need to find at least one of them. Same is true for minimum spanning trees. Now let's actually learn Prim's algorithm and apply it to this graph over here. And the good thing actually is, believe it or not, you pretty much already know Prim's algorithm, because we just learned Dijkstra's algorithm, and Prim's is actually almost exactly the same. It uses the exact same ideas. There's just a couple small variations. So given a graph, we typically want it to be in the form of an adjacency list so that for any given node, we can easily find a list of all of its neighbors. And with Dijkstra's algorithm, we wanted to always start from the source node. Like from this node, if we want to find the shortest path from this node to every other node in the graph, we would want to start at A. But for a minimum spanning tree, it actually does not matter which of these nodes we start at. We can start at any of them because we know the minimum spanning tree is going to include every single node anyway. So it doesn't really matter where we start because we're going to end up needing to include this A anyway. So we could run Prim's algorithm to find multiple things. One thing we could do is find the cost of the minimum spanning tree, or we could find the minimum spanning tree itself. That's what I'm gonna do. So given this graph, we're gonna find the minimum spanning tree, which is basically gonna be another graph. And we're going to represent that graph as a list of edges. So, maybe the graph includes AB, maybe it includes BD. So we would basically find the list of edges that make up the minimum spanning tree. Well, at least one valid minimum spanning tree. There might be multiple, who knows? But we're going to find a single minimum spanning tree and then return that list of edges. So in this case, we're going to start at A. And we're also going to be using similar data structures. We're going to have a min heap as well. On that min heap, we're going to have 3 values. The one that we care about the most is going to be the weight, because that's going to decide which, value we're going to pop first. We're going to want to pop the values with the smallest weight. And the next 2 are just going to be the edges. And the next ones are just going to be the nodes themselves. So essentially, if we were adding AC to this, we'd have AC. The weight of that is going to be 3. So that's, the 3 values we would add here. We're also going to have a visit hash set to make sure that we don't visit the same node multiple times, because that would essentially mean that we have a cycle, right? Because if we take A and then connect these 2 nodes together, this is our minimum spanning tree so far, and then maybe we connect B with that, then we have 3 nodes so far. And then if we somehow end up connecting A and B together, then we have a cycle, right? We definitely did not want to add the same node multiple times. So that's what the visit hash set is for. Now, starting at this node, what we would do is take all of its neighbors and then add that to the min heap. So we would take C, add that to the min heap. The weight of it is 3. The nodes are A, C. For B, same thing. The weight is 10 and the nodes are A, B. And at this point, the algorithm would run pretty much exactly like Dijkstra's algorithm. We could run the algorithm such that while the min heap is not empty, we're going to keep popping. But we could also have a different condition to continue the algorithm, which would be while the length of our visit hash set is less than the number of nodes, if that's a parameter that we're given, that would be one criteria to continue the algorithm. We also are going to be building our minimum spanning tree. That's going to be a list of edges, if you recall. So we could also code it up so that as long as the list of edges is less than n minus 1, because we know if we have n nodes in the graph, then we're going to end up with n minus 1 edges, which form the minimum spanning tree. And remember, visit is keeping track of the number of nodes, and MST is keeping track of the number of edges. So we kind of have 3 different conditions we could use. To keep it simple, let's focus on the condition where the min heap is not empty. So we're going to pop from the min heap the one with the smallest weight. So we're going to pop this one where we have nodes A and C. Oh, and by the way, before we even did any of this, since we started at node A would have been added to our visit set immediately. So now we popped this edge and we arrive at C. As soon as we do that, we're going to take C, check it's not already been visited. Okay, let's go ahead and visit it. And to build our MST, our minimum spanning tree, we would add this edge to the minimum spanning tree. Instead of writing all that out, I'm just going to, put a green circle to indicate this is part of our minimum spanning tree. So now we have 2 nodes in our frontier, just like with Dijkstra's algorithm. And we're going to continue the same way. But let me just go over a little bit on why this algorithm works. When we popped the edge with the minimum weight, we were essentially saying that we know in this graph, all nodes have to be connected together. A has to have a path to C. So there must be a path connecting these 2 nodes. And we know with 100% certainty that there's no such path that's going to cost less than 3, which connects these 2 together. Because the only other possible path that might connect them together, we don't know for sure, but in this case it does, there is a path from A through B that connects them together. So no matter what, to connect A and C, we would have to either directly connect them or we would have to go through B. Going through B is going to cost 10, which is more than 3. So there's never going to be a path that costs less than 3, which connects these 2 together. So the idea is similar to the shortest path algorithm. As we continue this and we keep then we're just going to skip it. But every time we introduce a new node, we're going to know for sure that we're adding that new node with the minimum possible cost it would take to add that node. So now that we visited C, we're going to add all of C's neighbors to the min heap because now we have 3 new edges that are reachable from C. So let's add all of them. They all have a weight of 4. So we'll add all 3 of them to the min heap. They all have a weight of 4. So C to B, C to D, and C to E. And by the way, even though we know that all of these edges are undirected, the order that we put these nodes does still matter because when we pop this, for example, we know that the second node is the one that we're actually adding. We're saying that this is the new node here, right? This is the edge, but this node already was a part of the graph C, but now we're adding the second node, which is B. Now, in this case, which one are we going to pop now? Because we can pop any of these 3. Well, who knows? Depending on the min heap implementation, we might pop any 3 of these. But it doesn't matter because regardless of which one of these we pop, we're going to end up with a minimum spanning tree because there could be multiple solutions. Just to illustrate that, if this was the one that we popped first, then our minimum spanning tree would look like this. We would end up adding these 3 nodes. But if we end up popping this one first, then we're going to end up adding these 3. Or maybe we end up popping this one first. In that case, we would end up adding these edges. Regardless of how we do it, we don't end up with a cycle and we end up minimizing the total cost. But let me actually prove it to you. Let's pick arbitrarily. This one is the one that we pop. So we pop this one, C to D. So we end up adding this node to our frontier essentially. So now we're going to take all of its neighbors and add them to the min heap. Well, at least all of the neighbors that haven't been visited. We have B, which has not been visited. So let's add that. That cost is going to be 1 to reach that. We could add C, but it's already been visited, so there's no need to do that. So instead, let's add the other one, E. It has a cost of 2, and that's basically it. By the way, we would also make sure to add D to the visit result, and this edge would be a part of our minimum spanning tree solution. Now it's probably clear to you why we're never going to end up popping the other ones that have a weight of 4. We're never going to end up adding these 2 edges because we just added 2 more edges that have an even smaller weight. And the good thing about these 2 edges is we're going to end up adding the remaining nodes that we need to. And then it's useless for us to add these redundant edges. So we pop the minimum from our min heap again. It's the edge with a weight of 1, D to B. So this node is now a part of our frontier. We're going to make sure to add B to the visit hash set. This edge is a part of our minimum spanning tree. And we're going to go through all the neighbors of B. Well, A has already been visited, C has already been visited, and D has already been visited. So we're not going to add anything to our min heap. Now we're going to pop one more time. We're going to pop this edge with a weight of 2, connecting D and E to each other. So E is a part of our frontier. We're going to make sure to add E to the visit hash set. And at this point, we know that we're done actually, because the size of our visit hash set is the same as the number of nodes in the input. But even if that wasn't the case, we would still, for E, go through all of its neighbors. While C's already been visited and D has already been visited as well. We would mark this as part of the minimum spanning tree. So essentially we found that this is one valid minimum spanning tree that we found for this graph. There obviously were others. Maybe we could have added, this could have been another minimum spanning tree, or maybe this could have been another minimum spanning tree. They would have all had the same total cost, but they could have been different. Now at this point, if we wrote the algorithm to keep running until the min heap was empty, we would still end up popping all of these. But what we would notice is that every time we pop, B in this case, for example, has already been visited before anyway. So that we would just skip that. We would pop this guy again, B has already been visited. These 2 edges were essentially, if we had connected B using this edge or maybe this edge, but we know that there was a cheaper way to do that. And we could have done that, for every edge until the min heap was empty, but we would have ended up with the minimum spanning tree regardless. And notice how we had 5, nodes, but the output that we created is 4 edges. It took 4 edges to connect 5 nodes to each other. That's our minimum spanning tree. Now, it's probably no surprise here that since the algorithm is so similar to Dijkstra's algorithm, the time complexity is going to be the exact same as well. In the worst case, we might end up adding E edges to our min heap, where E is going to be less than or equal to V squared, where, V is the number of vertices in our graph. Every time we push and pop from the min heap, it's going to be a log E operation. We might push and pop a total of E times. So this is the overall big O time complexity, but we know that E can be reduced to V squared, which can be reduced to 2 times V. And we know that we don't care about constants. So the overall time complexity would be E times log V. That's the time complexity for this algorithm. The memory complexity will end up being big O of E, because we have to keep track of all the edges, of course. That would be the max possible size of our min heap. Now, while this is definitely not an easy or trivial algorithm, the fact that it's so similar to Dijkstra's algorithm does make it, I think, manageable. If you can understand one of these algorithms, you will be able to understand the other algorithm. And it's no surprise that coding it up is also pretty similar. So suppose we're given a list of edges that make up this graph, and we're given n, which is the number of nodes in the graph. And let's assume, for simplicity, that the nodes are numbered from 1 through n. In this case, I gave each node a character as a label. That was just to distinguish, the nodes, which are characters, from the edges, which have, integer values. But the first thing we would want to do, given those edges, is build an adjacency list. So I'm essentially using a hash map for that. I'm going through integers 1 through n, and for each of those integers, I'm mapping that in the hash map to an empty array. And then I'm going through the actual edges. We know each edge in this case is going to have maybe a source and destination node. So for example, A is the source, C is the destination, and the third value is going to be the weight, so the weight of that edge. Now we know that each edge though is actually undirected. So when we add to the adjacency list, we're going to say this source we're going to say for this source, add an edge for the destination that has this weight value. But we're also going to say for the destination, add a neighbor node, which is the source, and give it the exact same weight. So basically C will be able to reach A and A will be able to reach C. And then in our min heap, we're actually not just going to add a single value to the min heap. Assuming we're starting at some arbitrary node, in the drawing, I chose A as a starting point. In the code, we're choosing the node that's labeled with a value of 1. We're going to take all the neighbors of that node and push the neighbors to the min heap. But we're actually going to have 3 values, just as I showed earlier. The first is going to be the weight. That's important because that's essentially the key of our min heap. That's going to decide which ones we pop first. Next, we're going to have the source node, which is essentially saying that, to get to C, we had to go through A first. So this is the edge that we're essentially adding, and the neighbor of A is C, and that's the node that goes last. And then we have our minimum spanning tree, which is an empty array initially. That's what we're actually going to return. That's going to be the list of edges that make up the MST. We're going to have a visit hash set. We're going to add 1 to the hash set because, the starting point has already been visited. And then we're going to run the algorithm while the min heap is not empty. We're going to pop from the min heap on each iteration. We're going to get those same 3 values that we pushed, the weight, the source node, and the destination node. If the destination node, in this example, C, has already been visited, then we're going to skip it. We're going to go to the next iteration of the loop. But maybe in this example, C has not been visited yet. In that case, what we would do is to the MST, we would add this edge. We would say the source was A, the destination node was C, so we're adding this edge to the output. We don't have to include the weight of the edge in the output, but maybe we could if that was part of the requirements of this function. But in this case, we're just building the MST, just the edges themselves, not their weights. We're also going to mark that node C as being visited, and then we're going to go through all the neighbors of C and then do the same thing. For each of those neighbors, if they haven't been visited, we're going to push them to the min heap. But one difference here between Dijkstra's algorithm is when we take the neighbors of C, for Dijkstra's, we didn't just add the weight 4. For example, if D is a neighbor of C, for Dijkstra's algorithm, we would take the weight that it takes to connect these together, the cost for that, and the cost it took us to reach C in the first place, because we wanted the shortest path starting from A to reach D, right? So we had to include the previous cost. But in this case, for the minimum spanning tree, we actually don't care about the minimum cost from the starting point to every other node that we add. We care about the total cost. So it doesn't matter what cost it took us before to get to C. This is part of our frontier at this point. So we want to minimize the cost it takes to add the remaining edges. So it's only costing us 4 to add this node. And then when we add this node, it's only costing us 1 to add B. And then it's only costing us 2 to add E. We don't have to consider the entire path every time we add a node. Because when we're talking about minimum spanning trees, we're talking about the total cost of all the edges themselves, not of any particular path. So here, when we push to the min heap, we're just taking the weight that it took for C to reach its neighbor. In this case, it was 4. And then we'd also push, E with the same exact cost and also B with the same exact cost. So that's the idea here. Pretty similar to Dijkstra's algorithm, as you can see. We definitely have a lot of setup here, but maybe in some cases you wouldn't need to, write out this code, because in this case we were just given the edges. Maybe you might be given the adjacency list itself. That would make it easier. That would mean us not having to write this code. The core algorithm is this portion here.